Okay, this is the end of the chapter. Did I miss something? Yeah, no? Okay. So we also have to worry about the sustainability of bioenergy, especially since it's being uh, relied on heavily under the future scenarios under RCPs. BECS, bioenergy and carbon capture and sequestration, is going to be a critical part of turning around our emission profiles and turning around the warming and to come down to removing enough carbon from the system. So it's not that we will emit zero, but we will emit some, but we will take out more than we emit, hopefully by 2050, 2060 horizons, and head to staying below 2 degrees, and God help us, maybe even below 1.5 degrees. Let's say a big game changer comes along and allows us to suck out carbon from the air and so on. But in the meantime, we still cannot get away from worrying about sustainable economic development as well as sustainable bioenergies with social equities and worrying about local environment. So this paper looks at the biomass feedback stock supply in that context in the economic, environmental and social phase space. So it worries about price levels, wealth creation, competitiveness and external costs intersecting with biodiversity protection, sustainable use of natural resources and climate change mitigation. And also with property rights, employment and social inclusion. So these kind of things are very common, but if you go to look at literature by people like Herman Daly, who was economist, thought about these ideas a lot for a long time and has written very nice papers and books. And his caution is that thinking about environment and social and economic spheres as separate with intersecting interests, he says we must remember that economy and social values and our existence all happen within the environment. So environment should be the big sphere within which economy and social equity and other things are thought of, not as external to the environment. That comes to very different decisions if you follow that thought process. Nonetheless, coming back to thinking about sustainability of bioenergy, this paper looks at integrated assessment approach to water resource model, ecosystem model, and BECS with land use. I won't go into the details other than to say that we actually need to worry about hydrological cycle and human interventions involved in BECS and how it competes with food production, for example, and of course irrigation and competition for croplands and ecosystem model where we worry about carbon stock, soil erosion, fire and so on. So tremendous details. And then land use model including socioeconomic scenarios. So we cannot get away from RCPs and SSPs in this case, and comes up with solutions like this for various SSPs. So doubling of irrigated land for biocrops. So there is agriculture and biocrop. So that's irrigated land. In S2 we go to biocrop on additional farmland, so there is more land but it is still farmland, and biocrop on converted forest land, so you are always looking at competitions between various land use types, of course, and on forest land being converted to bioenergy. So depend on various factors and reality checks and constraints. In that context, there is this detailed paper by Griscom et al. That came out in, I think, 2016 that looked in more details at these natural climate solutions that I already alluded to. And it talks about climate mitigation potential of 20 natural pathways with climate mitigation potential by 2030 in petagrams CO2 equivalent per year. And I'm going to not worry about the details of the numbers, but to point out once again that these are very much related to terrestrial biosphere. So land, role of the land in climate mitigation. So these are very critical. And it also looks at ambitions for less than 2 degrees C warming and low cost portion of the 2 degrees C ambitions, and with maximum safeguards. So you change the amount of mitigation with these options, and there are co-benefits associated here in terms of air quality, biodiversity, water, and soil function, and soil properties, soil health, for example. Okay, so without going into details again, I always keep saying that because each of these topics is so detailed that in the context of terrestrial biosphere as a part of climate mitigation, I can only give you a range of literature and approaches and studies that exist. So it has forests, agricultural and grasslands, and wetlands, has reforestation, avoided forest conversion, and so on. Has biochar, nutrient management, grazing and feed, conservation agriculture like tillage practices, etc., grazing management, and wetlands restoration. So coastal wetlands, peatlands, avoided peat impacts, and avoided coastal impacts, right? And this one puts this in the context of the targets we are aiming at as well, looking at global carbon emissions into the future, 2030 horizon and 2050 horizon. Business as usual would take us on this target in terms of emissions. The other RCP scenarios are in the middle. And then there is the contribution of the NCS natural climate solutions to mitigation to stay on this less than 2 degrees C pathways. So you can see that they can make a significant contribution to reducing emissions and bending the curve. This is what we mean by bending the curve. The business as usual scenario will take us here. There is an associated warming that's obviously going to blow past 2 degrees C warming maybe by 2030. And this is the NCS contribution. Okay, so I hope that gives you a kind of key messages about the role of land biosphere, especially in climate mitigation. But the negative emission technologies also have a huge role for terrestrial biosphere. So afforestation and reforestation obviously can help with negative emissions. Direct air capture technologies, which are not directly related to land use, but they are in the sense of where the carbon is going to be hidden. Is it going to be in the ocean or in the geologic fault lines or old oil wells and so on? So that also relates to competition for land use as well. Of course, bioenergy and carbon capture and sequestration, and enhanced weathering, as I mentioned, could also has to be on land. It cannot be done in the ocean. So land, obviously very critical for climate mitigation, and the success in terms of actually mitigating climate and achieving the full potential that we have been looking at requires monitoring biophysical, biogeochemical feedbacks and all the other socioeconomic factors and the required life cycle analysis and monitoring, reporting and verification of the carbon emissions and carbon sinks.